Recall the definition of ring homomorphism. We start with two rings, R and S. We assume multiplication is associative and that there are multiplicative identities, which we call 1. A ring homomorphism phi is going to carry R to S, satisfy the following 4 properties. So phi preserves addition, preserves multiplication, sends 0 to 0, and 1 to 1. With these properties, we can define the kernel of phi. So it's a subset of R, okay, all R and R, such that phi of R is equal to 0. Now note, phi of 1 is equal to 1, so 1 is not in the kernel of phi. And this is not going to be a ring by our strict definition. That's fine, it's going to be something else. Now, let's take a look at the big picture for group theory, group homomorphisms. If I have a group homomorphism phi carrying the group G to the group H, I could form the kernel of phi. That's going to be a normal subgroup in G. If phi is onto, we have the first isomorphism theorem of groups. So that says H is isomorphic to the quotient group G mod n. We have a similar procedure for rings. So if I have phi carrying R to S, a ring homomorphism, I could form the kernel of phi. Now, we noted this is not going to be a ring. This is going to be what we call an ideal. So this is going to be the analog of a normal subgroup. If phi is onto, we have the ring analog of the first isomorphism theorem of groups. So we have a first isomorphism theorem of rings. So that'll say, okay, the image ring S is ring isomorphic to the quotient ring R mod I. So this is what we're going to focus on for this part. To start, we begin with definitions. So a subset I in our ring R will be called an ideal in R. It satisfies the following properties. So it'll be closed under addition. It'll be closed under multiplication. But even stronger, I'll want, if R is an R, A is an I, then R times A is an I, and A times R is an I. And we sometimes call an ideal with both of these a two-sided ideal. We could define one-sided ideals also. Now, note, if we had 1 in an ideal, what happens? Well, with our condition 2b, I'll have that R times 1, which is equal to R, is an I for all R in the ring. So that would mean that we'd have to have that I is equal to R. For examples, singleton set 0 and the ring itself are always ideals in R. For non-trivial examples, we go to ring homomorphisms. So if phi is a ring homomorphism carrying R to S, then the kernel of phi is always a two-sided ideal in R. Let's run through the properties. So if A and A prime are in the kernel, we want to show that the sum is also in the kernel. We have by assumption phi of A equals phi of A prime is 0. So I want to show that phi of A plus A prime is also 0. Now if we apply the ring homomorphism property for addition to this, we could split it up. We get 0 plus 0 is 0. So first condition holds. For the second part, okay, this first statement is just that our ideal is closed under multiplication. It's actually implied by the stronger second statement. We just show this anyway, okay, same idea. I want to show that AA prime is in the kernel. If I apply phi, we could split it up using the homomorphism property for multiplication. I get 0 times 0, which is 0. So that holds. Same argument for the second part. If R is in the ring, A is in the kernel. Take the product, I apply phi. We could split it up. I have phi of R. We don't know what that is. But phi of A is equal to 0. So this goes to 0. That means R times A is in the kernel. Note for a two-sided ideal, I also have to show that A times R is in the kernel, and that's the same exact argument. So we have a two-sided ideal. Now, before we get to examples, let's clean some things up. We saw before that 1 is never in the kernel of a homomorphism. If we have 1 in an ideal, that means the ideal is the entire ring. To make that a little bit stronger, let's note that X is a unit in our ring. Okay, unit just means X has a multiplicative inverse. Then, if X is in an ideal, that means the ideal is the entire ring again. Now, if I pick any R in our ring, I want to show it's in the ideal. So note, if I take our unit X, that's in our ideal, I'm going to multiply that by Rx inverse, which is definitely in the ring. So by property 2, take this product, that's in the ideal. That's equal to r times 1, which is equal to r. So any element in our ring is in the ideal, so they must be equal. We have a similar statement for kernels of homomorphisms. So if I have a ring homomorphism, it must be non-vanishing on the units. We could show this directly. If I take x a unit, if I have 5x equal to 0, we use our definition of a ring homomorphism. The fourth part, phi of 1 is equal to 1. That's equal to phi of x inverse. We split this up. Phi of x is 0, and that means 0 is going to come out. So this says that 0 is equal to 1, contradicting one of our assumptions on the ring. We never have that 0 and 1 equal. Now, taking this one step further, if I have R a field, recall for a field, if you have an x that's non-zero in a field, it has a multiplicative inverse. So all the non-zero elements of a field are units. That means the only ideals in a field are going to be 0 and the ring itself. We also have, if phi is a homomorphism carrying our field to any other ring, the kernel has to be equal to 0. We have no other ideals. 0 or r can't be r because phi of 1 is 1. So that means every ring homomorphism from a field to any other ring is a 1-to-1 map. First example, let's consider ring homomorphisms between the integers and the modular integer z mod n, where n is greater than or equal to 2. We've seen there's only one ring homomorphism here that's given by sending the integer k to the residue class of k modulo n. Now, the kernel in this case is just going to be all multiples of n. So I write that as n times the ring z. If we could write our ideal as an element times our ring, then we just take that element and put it in parentheses. We'll say more about that next time. We can show that this is an ideal directly. So note, if I take two elements in here, say kn, k prime n, if I add them together, we get k plus k prime n, and that's still a multiple of n. So closed under addition. For the second property, if I take any element in the integers, call it k, multiply it by an element in our ideal, so a multiple of n, k prime n. Product is k, k prime n, which is another multiple of n. So we have our second stronger property. Note in this case, 1 is not a multiple of n. Another example, a lot like the one we have here. If I take the evaluation homomorphism from the rationals adjoin x, so polynomials in x with rational coefficients, we'll send this to q adjoin square root of 2. The map is just going to be take your polynomial f of x, send it to f of square root of 2. Now, we've seen this is a ring homomorphism. Kernel of E. How do we get to 0? Well, we're going to need polynomials that vanish on square root of 2. So we're going to be all polynomials that are multiples of x squared minus 2. Again, we have this situation where we have a single element times our ring. So I write this as x squared minus 2 in parentheses. We could show directly that this is an ideal, but that'll just be the same argument we have here. Now, for an example of an ideal that's not a kernel, we're going to use one-sided ideals. So let's take 2 by 2 matrices with entries in the real numbers. So we have A, B, C, D. Ideal 1 is going to have non-zero entries in the first column. Zeros otherwise. So you'll see here, this is closed under addition. If I take any 2 by 2 matrix, multiply it by a matrix in here, get back another matrix which just has non-zero entries in the first column, zeros in the second. So this is just going to be an ideal on the left side. I can multiply by elements of the ring on the left, and we stay in the ideal. On the other hand, take another ideal, I2. We'll have non-zero entries in the first row, zeros in the second row. Here, we can only multiply on the right to stay in the ideal. So this is going to be a right-sided ideal. A good exercise is to show that there are no two-sided ideals in the 2 by 2 matrices over the reals. getting back to generalities, we have the following proposition. So the following are equivalent. I is a two-sided ideal in R, not exactly equal to R, and I is equal to kernel of phi, where phi is a ring homomorphism from R to some other ring S. So this proposition clarifies the connection between kernels and ideals. Now, one direction we've already shown. If I have a ring homomorphism, its kernel is an ideal. So if I have an ideal that's not exactly equal to the ring, how do we get that as the kernel of some homomorphism? The natural way to do that is by considering quotient rings. Now, the idea here, okay, we're given a ring R and an ideal I. R has an addition and multiplication, and if we forget about the multiplication, what's left over? R is an abelian group under addition. We also have that I is a normal subgroup in R under addition, so I can form the coset space R mod I. So this is just group theory. Now, because we're considering the operation of addition, we have a way to add our cosets. So A plus I plus B plus I is equal to A plus B plus I. And this is well defined, meaning if we change the representatives, say to A prime and B prime, we get the same coset over here. So that's not something we need to check. That comes from old school group theory. What we do need to check, okay, so first, let's define multiplication. If I take A plus I times B plus I, okay, we FOIL, what comes out? We have AB, I times B is going to be a subset of I, okay, it's two-sided ideal. A times I is a subset of I, and I times I is also a subset of I. So if we work out the set product, what comes out is contained in AB plus I, and it might not be exactly equal to AB plus I. Regardless, that gives us an assignment of the product of these two cosets with another coset. So that's how we define multiplication. Now, problem, this might not be well defined, meaning if we change the representatives for this coset and this coset, we might get a different answer here. So let's check that. Now, we're going to switch representatives. So we'll assume A plus I equals A prime plus I, B plus I is equal to B prime plus I. We want to make sure when we take the product, we get the same cosets. So we're checking that AB plus I equals A prime B prime plus I. Now, if we interpret this, this is just saying A minus A prime is an I, B minus B prime is an I, AB minus A prime B prime is an I. Now, to show this, I take AB minus A prime B prime, and then we just have some abstract nonsense. So I can rewrite this as A times B minus B prime plus A minus A prime times B. The differences are an I, so the products are an I, and then the sum is an I. So this difference is an I, and our multiplication is well defined. Now, that defines our operations on the quotient ring. Okay, I'll leave the other ring properties to you to show. Now, what about the homomorphism? So the phi that I use, we're just going to take our ring into the quotient ring. I'll send R to the coset for R, R plus I. You have to verify that this is a homomorphism. Its kernel is just going to be I itself. So the only way that I get something mapping to the coset I is going to be if it was already in I to begin with. So that gives our proposition. Now, we have quotient rings, so we can state the first isomorphism theorem for rings. If we have pi, a homomorphism from R to S, okay, it's onto, I'll call I the kernel of pi. Then we have quotient ring R mod I. It's isomorphic as rings to our image ring S. The explicit map is just going to be given by, okay, so we're going to take the coset R plus I and just send it to pi of R. As before, most of our work is done if we ignore multiplication. Now, that means we're working with abelian groups under addition, we have a group homomorphism under addition, and we can invoke the first isomorphism theorem for groups. So that's going to give us the definition of our map. Okay, so this is well defined. It's one-to-one onto, and it's a homomorphism under addition. That means we still need the multiplicative properties to get a ring isomorphism. Now, using the definition here, okay, these properties are straightforward, so I'll leave them to you. Now, for examples, okay, we have pi carrying the integers to the integers modulo n. So we send each k to its remainder upon division by n. Now, the kernel here is going to be the multiples of n. So the first isomorphism theorem says quotient ring, z mod the multiples of n, so isomorphic to z mod n. Now, what are we doing here? We're going to take coset here, so say k plus the multiples of n. We're going to send that to the remainder of k upon division by n. So note, what's in here? We're going to have k, k minus n, k plus 2n. All of these numbers will have the same remainder upon division by n. So our map's well defined. They can check isomorphism, homomorphism properties. Similar situation holds here. We have the evaluation map carrying q adjoint x to q adjoint square root of 2. Okay, we've seen this maps onto. The kernel is going to be equal to the multiples of x squared minus 2. First isomorphism theorem is going to give us an isomorphism between the quotient ring and q adjoint square root of 2. Now, one thing we'll see later in here, each coset for this quotient ring can be written in the form a plus bx plus f of x. Okay, we're taking all multiples of x squared minus 2. So by this I mean, if we take any of these cosets, there's going to be a distinguished element, a plus bx. Now, when we evaluate, what do? We put square root of 2 in for x, so this part goes to 0. So every element in this coset goes to the same value, a plus b square root of 2. We finish with a familiar example. So we have phi carrying Gaussian integers, z adjoint I, into the integers modulo 5. Now, we define phi, okay, it's going to send a plus bi to a plus 2b in z mod 5. We've already seen that this is a homomorphism. For the kernel, we have all Gaussian integers, a plus bi, such a plus 2b is a multiple of 5. Now, this doesn't seem like a very tractable definition, but it turns out this is just going to be a set of all Gaussian integers that are multiples of 1 plus 2i. Now, how do we see this? The first step, we take our definition here and we start plotting points. When we've plotted enough points, we notice we have a lattice. Then the way we understand a lattice is to look for the points that are closest to the origin. So here they'll be plus minus 1 plus 2i, plus minus 2 minus I. We'll be able to pick a pair of generators from this set. Now, we note for this lattice, it'll be generated by 1 plus 2i and minus 2 plus I. That seems like we need two elements to generate our ideal, the kernel. But you'll note, if I multiply 1 plus 2i by I, we get minus 2 plus I out. So I only need one element to describe our kernel. Now, let's check that linear combinations of these in the integers satisfy the original condition. So I take x times 1 plus 2i plus y minus 2 plus I with x and y integers. Okay, if I work that out, we get an a and a b. I take a plus 2b and I get 5x. So this is definitely a multiple of 5. So that confirms that our lattice at least satisfies this condition here. Now, we go to the first isomorphism theorem. Okay, if we take the Gaussian integers mod our ideal, we get the integers modulo 5. So how should we think of this? Well, a natural candidate for our z mod 5, okay, we're going to mod out by these lattice points. So we have 0, 1, 2, 3, 4, and then 5 goes back to 0 if we're along the real axis. So that's one way to get our z mod 5. Another way to guarantee that we have representatives for each coset when we mod out by the lattice, I want to take all the Gaussian integers that are in this first square. So those are going to be, okay, we have 0, 1, 2, 1 plus I, but if we shift according to the lattice, we could push it to 3. 2 plus I, if we shift according to the lattice, we could push it to 4. Now, note, what's interesting is, okay, Okay, if we do our computations in the Z mod 5 or in the quotient, we always get the same answer in the Z mod 5. So for instance, if I took 3 squared, that's going to give me a 9, which goes to 4. On the other hand, I could represent 3 instead by 1 plus I. So if I square that, we'll get 2i. Okay, and then if we shift according to the lattice, we can go to -1. But that's going to be equal to 4 if we go modulo 5. So we know we get the same answer using different representatives.